Now let's discuss about ideal gas equation. The equation that we usually are exposed to before this, when we learn it in secondary school or when we learn in chemistry, is PV is equals to nRT. So let's go through again all the variables that are inside this equation. So P stands for pressure, as we mentioned just now, must be in Pascal or Newton per meter square. So make sure you convert it from ATM to Pascal. If it involves atmosphere, you know that 1 atmosphere is equivalent to 101,325 Pascal. So make sure you convert it to Pascal before you substitute it inside this equation. Okay, next variable we have volume. Volume must be in meter cube. So if you happen to have volume that is in liter, make sure you convert it to meter cube by using this conversion factor over here. So 1 liter is equivalent to 10 times 10 to the power negative 3 meter cube. Okay, next you have your temperature. Again, temperature must be in Kelvin. So you receive temperature that is in degrees Celsius. Make sure you convert it into Kelvin by adding 273.15 into the degrees Celsius value. Okay, so that's PV and T that we discussed in the previous video. Now let's bring your attention over here to the small n and the r. Okay, the small n over here represents the number of mole of gas molecules in the system. Okay, you can have 1 mole of gas, 2 moles of gas, or 3 moles of gas. So 1 mole of gas is equivalent to 6.02 times 10 to the power of 23 gas molecules. If you have 1 mole of gas molecule, it means that you have 6.02 times 10 to the power of 23 gas molecules inside the system. Okay, so mole is a specific quantity of gas molecules. Okay, so you can determine the number of mole using 2 different ways. First, you find how many molecules are there in the whole gas system. The total number of gas molecules in the system that is represented by big N. So if you know totally you have this many gas molecules and divide by the Avogadro number, which represents the number of molecules in 1 mole of gas, then you're able to get, for this system, how many mole of gas do you have. Total number of gas molecule, 1 mole of gas molecule, 1 mole of gas got how many molecules? Take this, divide this, you get number of mole of gas molecule. Okay, this is chemistry. Okay, you learned about it in chemistry before. Okay, another way of determining the number of mole is to get the total mass of the gas system. Let's say the mass of the gas system is 64 grams. Okay, you know that this is oxygen gas. Oxygen gas, let's say, total has 64 grams of gas. Then you know that each mole, there's 32 grams. Okay, each mole, the mass of each mole of gas, oxygen gas, is 32 grams. So that's a molar mass. So if you get 64 grams, divide by 32 grams, you get 2 mole. That means there's a total of 2 mole of gas inside that container. Okay, so you can get the total mass of the gas system, divide by the molar mass of the gas system of the gas, then you can obtain the number of mole of gas molecule. Okay, so that's number of mole. Then R here represents the universal gas constant or the molar gas constant. In our physics syllabus, we define R to be 8.31 joule per mole per Kelvin. I'm aware that if you learn it in chemistry, it's a different value, 0.08206, something like that. Okay, I'm not sure the exact value. Okay, but because we are keeping our pressure in Pascal, our volume in meter cube, and our temperature in Kelvin, because we set this to be the unit that we use for PV and T, that's why we need to modify our gas constant R to be this value over here, which is 8.31 joule per mole per Kelvin. So this is the gas constant that we'll be using in this chapter. Okay, so of course, just like I mentioned that this ideal gas equation has another version of it. You can create another version by taking the number of mole over here to be equals to the total number of gas molecules divided by the Avogadro number. This is what we discussed over here. By taking this small n, using this conversion factor, you are able to change it to n over Avogadro number over here. On the other hand, this gas constant over here, R, is equals to K multiplied by the Avogadro number. So if you replace this small n with n over Na, if you replace this big R here with K and A, you can essentially obtain this new equation, which is PV is equals to NKT. Okay, they are both called ideal gas equation, and they are both interchangeable between each other. You can use any equation that you prefer, but if usually your information regarding a gas system is mostly on molar, in molar terms, okay, 1 mole of gas, 2 mole of gas, most of your information are in molars, then it's better to use this equation. Okay, but if your information given to you are mostly on on every single gas molecule, what's the mass or what's the total number of gas molecules. If your information are heavily centered around gas molecules, then you can use this equation, PV is equals to NKT. If it's mostly focused on molar cases, then it's PV is equals to nRT. But again, using both equations should give you the same answer. Okay, just that it's more suitable. There's different situations where each of these equations are more suitable to be used. Okay, so if we use PV is equal to NKT, then the big N over here represents the total number of gas molecules in the system. So usually this N here will be a very big number. Let's say if I have 3 moles of gas inside, then that's how many gas molecules do I have? I have 3 times of 6.02 times 10 to the power 23 gas molecules. Okay, so usually it's a very big number, times 10 to the power 23 times 10 to the power 24. It's a significantly big number because that's the total number of gas molecules you have inside the system. Okay, the total number of gas molecules inside the system can be obtained by taking the number of mole, just like what I said just now, 3 mole of gas. Each mole has 6.02 times 10 to the power 23 gas molecule. So if you multiply them, you get the total number of gas molecules in the system. Okay, you can also obtain this number of gas molecules here by taking the total mass of the gas system. Let's say 32 gram of you have 32 gram of gas, oxygen gas. You divide by one single gas molecule, one single oxygen gas molecule. What's the mass of it? Okay, so if you divide it, you are able to get how many gas molecules you have in the system. Okay, so it's similar to the equation for number of mole, just that you have to be aware that we are flipping the order over here between big N and small n, whereas this one you're dividing by the molar mass, but for big N you're dividing by the mass of one single gas molecule. Okay, next you have your Boltzmann constant. K here represents Boltzmann constant. Certain books they write it as K subscript capital B to represent Boltzmann. K subscript capital B. Okay, it's a differentiate between spring constant and Boltzmann constant. Okay, so the value for Boltzmann constant is 1.38 times 10 to the power negative 23 joule per Kelvin. Then actually how do you obtain this value? You obtain this value by bringing the Avogadro number to the left. So you take 8.31, the gas constant, divide by the Avogadro number, which is 6.02 times 10 to the power 23. Then you get a Boltzmann constant, which is 1.38 times 10 to the power negative 23 joule per Kelvin. Okay, so you can use each these two equations. Both are usable, but different contexts, different equations are more suitable. Okay, so make sure you get the constant right, and of course, if they don't give you a number of mole or the number of gas molecules, you have to find it using this kind of relationship over here. Okay, so K here of course is R divided by Avogadro number, so you can try to calculate yourself. You get 1.38 times 10 to the power negative 23. And lastly, you can see that the Avogadro number can be used to relate the mass of one single molecule and the molar mass. Because if you take the mass of one single molecule, multiply by the number of gas molecule for 1 mole, you get the mass for 1 mole of gas. Okay, so this is again chemistry. If you're not really sure what I'm trying to talk about regarding these 3 equations, I hope that what you can do is sit down, take a piece of paper, try to draw the situation. If one gas molecule, the mass is small m, then Avogadro number, it's 1 mole of gas, number of molecules in 1 mole of gas. Then if you multiply it, you get the mass of 1 mole of gas. So mass of 1 mole of gas is actually just molar mass. Okay, so take a paper, sit down, draw a situation to make sense of this equation over here, then it will really be helpful for you. Okay, but for now, this is ideal gas equation.